multiple comparisons, which he'll be speaking about today in statistical genetics. He has worked collaboratively with so many investigators in cardiology, infectious disease, pulmonary, nephrology, oncology, and health services. And just to note, he also completed a master's in statistics at Iowa State and a BS in physics at the National Taiwan University. So Chi-Hong, welcome, and thank you for joining us.
Well, thank you. Thank you for the opportunity to discuss this multiple comparison issue today. I'm gonna share my screen. Okay. So today we are gonna talk about multiple comparison problem, and we'll start out with like Bible code prediction story. So in 1994, the Journal of Statistical Science published this paper, the equidistant later sequences in the book of Genesis by these three authors. And this paper is about statistical analysis of this Bible code. And so let's first look at the equidistant later sequence. So what is equidistant later sequence? So an equidistant later sequence, ELS, of length k is a subsequence. So gn plus d to gn plus k minus d. So is nth later and n plus d's later to the last one is n plus k minus d, k minus 1 times d laters, where the laters in some range. So for example, in a page, right? And the quantity d is called skip, and it can be positive or negative. So when it is positive, it's the sequence is going forwards, and when it is negative, it's going backwards, right? So here is an example, right? So if we look at this purple circle, TENN, so that's an equidistant later sequence, right? And here we have the red circle, MLKING. Okay, that's also an equidistant later sequence. And then there's a to be killed by them. And then we have these GUN and GUN here. And then these, the green circle is prepare for death, right? So these are all equidistant later sequence, okay? And so the idea is that in the Bible, there's this hidden message, and it's formatted in this equidistant later sequence, okay? So the Bible code is also called Torah code. It's a purported set of secret messages encoded within text of Hebrew Bible and describing prophecies and other guidance regarding the future. Okay, so for example, by taking every 50th letter of the book of Genesis, starting with the first Tau, the Hebrew word Torah is spelled out. So in a way that the Bible code is a structure in the format of equidistant later sequence, and is hidden in the Bible and for people to find out. So that's the idea. So what does this paper is doing? So they are doing this experiment. So the first, they pick the list of word pairs. Okay, so it's a names and days of birth or death of famous rabbi based on the Encyclopedia of Great Men in Israel. So they pick an encyclopedia and they find the name, the rabbi's name and their birthday or death day. Okay, and in the book of Genesis, they search the equidistant later sequence that matches the name and date of birth and death of these famous rabbis. Okay, and their hypothesis is that equidistant later sequences spelling words with related meanings often appear in close proximity. So that means that the names of the rabbi and the birthday or death day of rabbi should be relatively close in a page or something, that that in the book of Genesis. Although they don't show exactly what it is, they show in the format of this equidistant later sequence. Okay, and what they do is they want to test this hypothesis, and they use permutation tests to test this hypothesis. And this is what they find. So they do the permutation test and they get a p-value equal to 0.000016. So it's very significant. It's very significant. So this sort of suggests that there's some hidden message in the Bible, right? And so the editors, this is what the editor says. So the statistical science is one of the top journal in statistical research. And the editor said that our referees were baffled. Their prior belief made them think the book of Genesis could not possibly contain meaningful references to modern day individuals. The paper is thus offered to readers as a challenge puzzle. So look at the paper, it seems everything is doing correctly, and they have this surprise finding. And so they are a little surprised and confused. So the paper is offered to readers as a challenge puzzle. Okay, so that's in 1994, and in 1996, finally, there's another paper, the published in Statistical Science, solving the Bible code puzzle. Okay, and so this is the case. Okay, so this paper said the data was very far from tightly defined by the rules of their experiment. So there was enormous wiggle room available. Okay, so for example, in the choice of names of the famous rabbis, so it turned out that the Hebrew language seems to be a very flexible language. They have many ways to say the same thing. Okay, so for example, the John F. Kennedy, so there are many ways to say the names. The Jack Kennedy, JFK, Mr. President, Mr. J. Kennedy, or the man who accompanied Jackie to Paris. So there are many, many ways to say the names. And also, there are many ways for the choices of the day form, okay? And they also have substantial choice in other aspects of the experiment, including the method of analysis, okay? And the author conduct the analysis, they find a similar significant result can be found in War and Peace. So they do the same experiment, allow the same enormous around the wiggle room. They can demonstrate there's a significant association between the names of rabbis and the birthday or death day of rabbis in War and Peace. And the author also demonstrated that they can find their own names and birthdays in the Bible. Okay, and so this seems to be okay. So the editors said that the specifications of the search of hidden words were in fact inadequately specific. Just as in clinical trials, it is essential to have a strict protocol, and deviation from it produce many more opportunities for surprise patterns. And choice of the words to be discovered may seem innocuous, yet be very consequential. And so there's a good reason to think that the particular forms of words those authors choose effectively tune their method to their data, and thus invalidating their statistical tests. So in other words, they look at the words in many different ways. And so they look at data in many different ways, and somehow they justify themselves and pick the words, the format of words, and also the analysis that was consistent with their hypotheses and reporting the result. Okay. And this seems to be a little bit extreme, but it's actually happening a lot in statistical analysis. So in the statistical analysis, we have a lot of choices to be made. Like, for example, choices of endpoints. When we get the data, oftentimes it consists a lot of endpoints that we can analyze. And we probably analyze all the endpoints and we pick the one that finds some significant or interesting finding and report it, right? So there's a choices of endpoints that we choose to report. And in the analysis, there's also the choices of the forms of endpoint. So either we use continuous variable or we dichotomize the variable. And sometimes we compare the highest quartile versus the lower quartile, right? And sometimes we make some transformation. So these are all choices. And sometimes we look at these different options in the analysis and pick the one that we think that's reasonable and report it. And we also have a lot of choices of the data inclusion, exclusion criteria. So we can, sometimes we arbitrarily choose the data cutoff date. And we sometimes identify certain data points as outlier and remove them. And we also include or exclude data based on the subject's compliance to treatment. And also the missing data. A lot of time we just ignore the missing data, or we only analyze with certain subgroups, right? So these are all choices we make in the statistical analysis. And for the statistical method, there are also a lot of choice. So for example, if you have missing data, so how do we handle the missing data? Do we do the imputation method, or we just ignore the missing data? We just only do complete data analysis. So, and also like the analysis methods such as t-test, Wilcoxon test, regression analysis. So a lot of time we have some room to pick one of them as our analysis. And choices of models. So what models, what covariates to include, right? Do we do model selection? So we have a lot of choices in this statistical analysis, and we human beings are very good at explaining things away and justify ourselves. So that may lead to some surprising findings. Okay, and so effectively what this does is it produces a lot of noise in the literature, because a lot of paper that were produced that nobody can reproduce, because those are, for example, based on, we look at multiple outcomes and we pick the one that was significant. So a lot of times people couldn't reproduce that. So this is one of the reports on reproducible research. So it's published in Science in 2012, and it's open science collaboration. And the purpose is to estimate the reproducibility of psychological science. Okay, so what they do is they pick about 100 papers from 3 top psychological journals. And these paper doing some experiment. Okay, so they were 97 papers. They find significant association or effect. And when they try to reproduce them, only 35 of them they can find statistical significance. So that's the first line overall. Okay, and the percentage they can reproduce is 36%. And in the original paper, the mean effect size is 0.4, and with the sample size 50, the median sample size 54. And when they try to reproduce it, the mean effect size in the replication is 0.197. So it's about half of the original effect size. And the median replication sample size is 64. So it's a little bit bigger than the original sample size. And they also estimate power. So if the original effect size is true, they should have about 92% power to detect the significance, right? But in fact, they only find 36%. Okay, and that's the first line, and the other 4 lines is breakdown by the 3 journals. and by different field of the psychological science, like either it's a social psychology or the cognitive psychology. And it seems they all show that relatively low percent of the reproducibility. Okay. And so another report in Nature 2016, they surveyed 1,500 scientists and asked them about reproducibility. So the question they asked is how much published work in your field is reproducible, okay? And so this is basically a histogram, and 0% is at the bottom and 100% is at the top. Okay, and the first one, so it's by different field. And in chemistry and physics engineer, it seems the reproducibility that people think is pretty high, maybe like 80%. Okay, earth and environmental science, it's probably, they are more like lower percentage. And biology is a little bit lower, and medicine is here. So it's probably a little bit over 50%. And this is other field. So it seems the problem is very prevalent, and everybody knows about it. And of course, that the reproducibility problem is not only due to multiple comparison, but it's also possible due to other reasons. For example, like confounding and other experimental design issues. But here, the Steve Goodman in this paper in Science Translational Medicine said that multiplicity combined with incomplete reporting might be the single largest contributor to the phenomenon of non-reproducibility or falsity of published claims. So what does that mean? That means that people maybe take a multiple look at their data and they didn't say it. They just say it as if that's the only outcome they look at, and that's the only analysis they carry out, and they have this finding. So it's possible that people have multiple attempts on the same data set, and they report what it is significant or consistent with their belief. So that's the problem. So the incomplete reporting and multiplicity actually probably produce a lot of noise in our scientific literature. Okay, so next, so let's talk about how do we handle hypothesis testing or multiple hypothesis testing in the statistical analysis. So in the statistical analysis, we in the hypothesis, particularly in hypothesis testing context, we generally formulate these null hypotheses and alternative hypotheses. So for example, the null hypothesis says that the treatment has no effect, and alternative hypothesis says that the treatment has some effect. Okay, and these go into this fourth scenario, right? So here either we have a null hypothesis true or alternative hypothesis true, and so that's the truth. And in our action, either we accept null hypothesis or we accept alternative hypothesis. Okay, so when the null hypothesis is true and we accept null hypothesis, we are doing okay. Okay, and on the other hand, when the alternative hypothesis is true and we accept alternative hypothesis, we are also doing okay. And we make errors when the null hypothesis is true, we accept the alternative hypothesis, and we call it type 1 error. And we also make another kind of mistake is that when the alternative hypothesis is true and we accept the null hypothesis, and that's the type 2 error. So this is the framework that hypothesis testing is doing. We try to control the type 1 error rate. Usually it's like 5%. So here the type 1 error rate is alpha, usually it's a 5%. and which is defined by the probability of accept alternative hypothesis when no hypothesis is true. So the bar here is condition. So it's a when alternative, when no hypothesis is true. So this probability is alpha. And the type 2 error rate is beta. And so it's the probability of accept no hypothesis when alternative hypothesis is true. And that's beta. And the power is 1 minus beta. So that's the when the alternative hypothesis is true, that means there's a treatment effect. And we actually say that we actually find there's a treatment effect. And so that's the power. And so when we have multiple comparison, which means that we test M hypotheses at the same time, okay? So if we control type 1 error rate, so this is a false positive rate at 5% for each individual hypothesis. If we have 20 independent tests, then the overall type 1 error rate is 64%, okay? And if we control, at the same time, if we control type 1 error rate is 5%, and with 100 independent tests, then the overall type 1 error rate is 99%. So which means that if you have one data and you look at the data in the 20 different ways, most likely you have 64% of chance to find something significant. And similarly, that if you have if you are able to look at the data 100 different ways, then you probably almost surely you will find something significant. So the overall type 1 error rate is 99%. Even there's nothing, it's all random in the data. So one way to handle this is to use Bufferoni correction. And so what the Bufferoni correction is to control type 1 error rate. Instead of alpha, we control it at the alpha star. So it's alpha divided by M label, right? So for example, if you have 20 tests, then we control the type 1 error rate for each individual test at 5 divided by 20%, right? And so if we do the simulation with 20 independent tests, the overall type 1 error rate, we maintain the overall 5%. So the Bufferoni correction works. And the same for 100 tests. With 100 tests, the Bufferoni correction say that we need to control individual tests at the 5 divided by 100% level. And so these will allow, so what this does is that with 100 independent tests, the overall type 1 error rate is also about 5%, it's 4.9%. So Bufferoni test works very well with independent tests. And it's also very easy to do because you just look at the number of tests and you took the 5% divided by number of tests, and you know that's the significant label that you need to, you can declare. In general, it's very conservative that if you have correlated hypotheses. It works very well for the independent test, but it becomes very conservative for the correlated hypotheses, okay? And there are also other methods to correct for multiple comparison to control for the overall type 1 error. And so they are a little bit complicated. For example, CDAC correction, and they control the alpha star by this formula. So 1 minus alpha to the 1 over n. This is very similar to Bufferoni correction. And there's another one is home step down procedure for p-values of m-tests. This also control for overall type 1 error, right? And so this is the p star. So what they do is that you have to sort the p-value of the multiple, the m-tests, okay, from p1 to pn. And you declare, you correct for the p-value. So the p star I is equal to pi times n minus I plus 1, okay? So here you correct your p-value, okay? And they all have very similar to, power to Bufferoni correction. So most people would just do the Bufferoni correction. Okay. So another way to control for like to handle the multiple comparison is to control, instead of type 1 error rate, we control for the false discovery rate. Okay. So this is the same table that we see before with the truth, no hypothesis true, alternative hypothesis true in the rows. And the column is accepting no hypothesis or accept alternative hypothesis. With the total of M tests. So we have M0 tests, they are the no hypothesis true, and M1 of the tests, the alternative hypothesis true. And we accept U of the tests of those no hypothesis true, and V of those with alternative hypothesis true, and total is we accept the S alternative hypothesis, right? So M equal to M0 plus M1, and here there's a S test we find significant, and M minus S test we accept alternative no hypothesis. We didn't find it significant. So how does this compare to the controlling for type 1 error? So controlling for type 1 error out of M test, we control for the probability of this U, okay? So the greater than 0 equal to alpha, so like we don't allow any of this U happen. Almost, we allow 5% that there's some U over here. And controlling for false discovery rate, so what we do is we look at the expected value of the U over S. So we can think of S is the total discoveries, and the number of U is false discoveries. So we only look at those, here we only look at these out of total discovery. We allow 5% of them or alpha percent of them to be false. So we allow U false discovery rate. So the percentage is alpha, okay? So that's for the false discovery rate. Okay, and there are some simple procedure to control. So false discovery rate is a little bit more relaxed than the controlling for the type 1 error. Okay, and so there are some simple procedure to control for false discovery rate. And so here is the Benjamini and Hatchberger procedure to control false discovery rate. So that, so we first, what you do, the first step is you have like M tests and you produce M p-values. So we have M p-values and we sort it of P1 to Pn, where P1 is the smallest one and Pm is the largest one, okay? And that alpha, so we define alpha to be the significance level or FDR level that we desire. So typically is 5%. For one tail or 2.5% for two tail tests, okay? And the procedure compare PM with alpha. So with the largest one, okay, with alpha, and PM minus 1 with alpha times M minus 1 divided by N, okay? And you keep doing this with P1 with alpha divided by N. And we're stopping the comparison with the first J, such that Pj less or equal to alpha times J divided by N, okay? And all tests associated with P1 to the Pj are declared significant, and all tests associated with Pj plus 1 to Pm are declared non-significant. So the first Pj, the smallest Pj, you declare significant, and the other you say they are non-significant. So based on this procedure, that it is demonstrated that we can control the false discovery rate at the alpha level. So this is an example. So for example, this is the first column is the p-value we produce for each test. Here we have 10 tests, and the p-value are 0.01, 0.02, 0.04, 0.06 to 0.05. right? And we sort it in this order, okay? And so FDR, what FDR do is we compare this we compare this p-value to this number. So 0.05 times j divided by 10. So for the first one is 0.05 times 1 divided by 10. So we compare to the 0.005. And the second one we compare to 0.01. And the third one we compare to the 0.015. And to the last one we compare to the 0.05. And it seems that all the p-values are smaller than their thresholds. So they were all significant in the FDR, controlling for FDR. And so the third column is that for the Bufferoni correction, we compare to 0.05 divided by 10 because there are 10 tests, right? So we compare the p-value to the alpha label of 0.05 divided by 10, which is 0.005. And so here we find 3 significance and all the others are non-significant. So Bufferoni correction is more stringent and FDR is correction is much more relaxed. Okay, so we understand that people, you know, the researchers they have pressure to publish it and then get funding. So let's look at some practical issue. How do we do multiple comparison? So the first is when to do multiple comparison adjustment. Okay, so this is the sort of current acceptable way that to handle multiple comparison. Okay, so there are 2 things you look at. The first, you look at the nature of study. Is a natural study confirmatory or exploratory? So if it's a confirmatory study, you definitely want to control for multiple comparison. However, if it's an exploratory, maybe you have more flexibility not to do that. Okay, and the second one is relationship among these multiple hypotheses. Are they related? If they are related, you definitely want to control for multiple comparison. If they are distinct, this is a little bit controversial that there's no consensus about this. Okay, so let's look at some example. So for example, your study is a pilot study, phase 1 study, phase 2 study. We probably consider them as an exploratory study. So you probably don't need to control for multiple comparison. Okay. However, if it's a phase 3 study, so pilot study, I think people understand. And phase 1, 2, 3 is in the drug development study. So the phase 1 is dose finding, and phase 2 is initial efficacy assessment, and phase 3 is the final FDA approval study. Is generally is a randomized study to confirm that the treatment is effective. Okay, so in the phase 3 study, you definitely want to control for multiple comparison. But however, for the pilot study, phase 1 and phase 2, when you report it, you probably don't need to control for the multiple comparison. Okay, and again, for the primary versus the secondary endpoints. So in the primary and not the primary endpoints, if you declare that these endpoints are primary endpoints, you definitely want to control for multiple comparison. However, if it's a secondary or exploratory endpoints, you probably don't have to control for multiple comparison, okay? And the next one, okay, you have 3 treatments. So for example, high dose, low dose, and no medication. Do you think you need to control for multiple comparison? When you compare high versus no, and low versus no medication? You probably do, because they are related, right? So relationship among the hypotheses is they are sort of related hypotheses. It's just different dose. So you probably need to control for, you definitely want to control for multiple comparison. And the treatment of vitamin D, fish oil versus placebo. So this is a little bit controversial. Like, so for example, here we have two comparisons, vitamin D versus placebo and fish oil versus placebo. Some people consider them as two separate experiments. And so you don't need to, they think it's okay not to control for multiple comparison, just report individual results. But some people think that it's still in the context of multiple comparison problem, okay? But sometimes you can get away with not doing multiple comparison. So this means that the vitamin D effect and fish oil effect are probably, there's no relationship with each other. And outcomes of MI, stroke, and death, so in the cardiovascular disease. So you probably need to control multiple comparison because they are related hypotheses. And outcome of the cancer incidence and cardiovascular event. So if we think that these two kinds of events are independent, they are not related with each other, they are just like two experiments, some people think that you don't need to do multiple comparison, but yeah, but there's no consensus on this one. Another one is the longitudinal outcome of A1C at 6 months, 12 months, and 12 months. So this is all A1C at different time point. So they are definitely related. So you need to control for multiple comparison, okay? And outcomes of interim analysis. So interim analysis is usually that we conduct interim analysis when the data collection is halfway, right? So it's certainly related to the eventual analysis, so the final analysis. So you want to control for multiple comparison. And for sensitivity analysis, generally people consider this as exploratory, right? So you don't need to factor the sensitivity analysis into your multiple comparison. Okay. And the next question is how to avoid it. Like sometimes you have a limited budget and you think to do multiple comparison is just not realistic. So one way is you pick one primary endpoint, okay, and leave all other the endpoints of interest as secondary, right? So in this way, you only have one hypothesis, then you don't have multiple comparison, right? And the second one is create composite endpoints. So for example, you want to consider MI, stroke, or death simultaneously. So what you can do is create a composite endpoint, which is whichever happened first as the endpoint. So you combine all of them as a composite endpoint. The third one is create a summary score. So sometimes you have different scales and you just do the average as a summary score. So for example, the physical function score in SF36 is a summary score of all different domains of the physical function, right? So that way you only have one endpoint. And the last one is that if your sample size is really large, so sometimes you can try this, you do split sample. You split the sample into two parts and you use one part for hypothesis generating. So which means that they say that you have 100 hypotheses and you use one part to evaluate these 100 hypotheses and pick the most promising 10 hypotheses. And then use the second part to test these 10 hypotheses. So you reduce the number of the multiple comparison, right? So you only test for 10 hypotheses instead of 100 hypotheses. So if you have a big sample, maybe this is you can consider this. Mm-hmm. So that's all I have to talk. This is about multiple comparison. I would be happy to take any questions.
Terrific. Yeah, thank you, Chi-Hong. So yeah, any questions from the audience on this?
Hi, thank you very much. Great presentation. Very much enjoyed it. I had two questions. The first one was, if you could go back to the FDR, I think you were mentioning that the false discovery rate was actually another alternative. I'm just wondering, is it, how would you compute the confidence interval, when you're using like the FDR, or would you just specify it and the software will do it for you? That's the first question. And the second question is, I've come across like other methods that they've mentioned that could be used when we have multiple comparison, such as semi-Bayes and hierarchical modeling for dealing with that. I don't know if you have any experience with that, or if you have any preference also using those type of methods.
So that's a good question. So the first question is the confidence interval of the estimates when you do, after you do the multiple comparison. So that's a very good question. Yeah, that's a very good question. So generally, I separate these two things. One is hypothesis testing, and one is point estimates, right? So the hypothesis testing is we try to find what's significant controlling for the type 1 error, the error we mistake. And the point estimates is we estimate the effect. So you are right in terms of the, it seems that if you have like multiple endpoints, maybe we should consider some kind of simultaneous confidence interval, right? Most people don't do that. So most people, they probably would just do the 95% and maybe you also report 99% confidence interval. Right?
Oh, I see. Okay.
Yeah.
Okay.
But sometimes people do this simultaneous confidence interval. For example, if you have a curve, right? And so you have a lot of estimates at different points. And people do use this envelope to sort of cover 95% of the curve estimates. And then that's a simultaneous confidence interval. Right? So that's a good question. Most people don't do that for the reporting point estimates. We probably just report like 95% and 99% confidence.
Okay, thank you.
Yeah, I don't have for the second question. I don't have a lot of experience with other Bayesian methods and to do the multiple comparison, but I think that's worth exploring. Yeah.
Okay, thank you.
Thank you. Yeah.
So can I ask a question?
Sure.
Well, first I didn't want to do a little comment. I don't think your example in 24 is the best for SF36 physical function, just because it's 10 items and it's unidimensional. So I would just use physical component summary score instead, where that is a combination of different scale scores.
Right. Yeah, I think that's what I mean. Yeah.
Yeah, because it sounded like that's what you're describing.
Right.
But I guess when you first introduced this, you talked about all these decisions you could make, like missing data and all the analytic decisions. And it also relates to what you've talked about, the main presentation, which I think is just absolutely fantastic. But a lot of this, doesn't it kind of boil down to what's kind of difficult is you never know what the reviewers are going to want. So some reviewers are going to, whatever you do, like let's say you decide you're not going to adjust at all, and then they say you should do Bonferroni, and then everything becomes non-significant. I mean, I guess part of this is how you can argue back against that, because there's checks and balances on all decisions, and if they're good reviews, they're good feedback, but they're also balanced. They don't say you absolutely have to do it this way unless they're really correct.
Right. Yeah, that's a very good point. Yeah, I would say probably something we can do is more complete reporting to handle this. So which means that we have a strict protocol before we do the analysis, and this is we follow. And if the reviewer want to see other analysis, we can certainly, I think we have to do in order to publish. And but we have to just declare it. This is our original protocol, and this is the reviewer asks us to do. So we do additional analysis. Yeah, I think most of the problem of the multiple comparison or multiple look at the data set or do the analysis in multiple way that creates error is this complete reporting problem that we look at many different ways, but we only report one of them. Yeah.
Yeah, so that, well, I mean, often you try to do that though, right? You say, you try to anticipate and say, well, if someone thinks it should be done this way, we could go ahead and say, we looked at it and it doesn't matter, or else you wait until they say it and then you evaluate it. It's kind of,
Oh, that I think you should say if you look at it.
no, I know, but I'm just saying what's the best strategy. It just depends sometimes, right? Like if you don't want to adjust for multiple comparisons, you think your tests are related or not, whatever you want to argue, and it confirms what you're doing. You could also say, well, someone else may not agree, and I'm going to go ahead and look at the way I think they may look at it. Or you could wait until you get a review that says you should do it that way.
I see. Okay. Yeah, I think that if we have a strict protocol, then the primary analysis will be based on the protocol. And then of course we can do sensitivity analysis, right? So we can report all kinds of sensitivity analysis and report them. Yeah, I think that's the best way of handling it, that this is what we, this analysis is what we set out to do. But for other consideration, these other things are the sensitivity analysis.
Yeah, that's great. Thank you.
Yeah, I don't know if anyone has another question. I have another question.
Okay.
Yeah, I'm just wondering, so is the false discovery rate I guess if you were to choose between all methods, would that be the top choice that you will recommend?
Yeah, okay, so that's a good question. So false discovery rate is a little bit more relaxed. So which means that it actually allows a little bit more error than controlling the type 1 error. So I think if you want to demonstrate that, I would rank the Bufferoni method is more strict. It's actually a better one than the false discovery rate because it just allows a little bit more errors. Yeah.
I see. Okay. Yeah. Thank you very much. Yeah.
But you are right. Both of them control certain kind of errors. Yeah. It's just different degree of the controlling.
Okay.
Well, one strategy I've seen is that sometimes people, including myself, will want to say, we realize that 5%, is significant by chance alone. We've done 10 tests, so, you can't trust every one of these, but at least we're, it's likely it's only one, let's say, or something like that. Try to argue that you don't want to be too conservative and take away the potential for there being something and realize that you shouldn't overinterpret what they're presenting.
Right. Yeah, I agree. I think that's also like fall into the category of like complete reporting, that we actually, look at 10 things, and this is we find at the 5% level. Yeah. And we can report that all the other that has no significant findings.
So I guess another question for me, Chi-Hong. So it would make sense. I mean, now that we're moving into online journals with kind of more room for appendices, to be able to put all of this in there.
Right. Yeah.
Which was harder before. But I guess if you've been on papers that have been, or just good examples of how to do this kind of reporting, is there like a template or a certain way that
I see.
one should do it?
Yeah. So there are I think, yes, there are some reporting guidelines. Is that what you are asking?
Yeah, more or less.
Yeah, I think there are some reporting guideline people suggest out there. Yeah, I don't have a template, um, but I would say is again, you have a protocol before you do the analysis, and then everything you refer to the protocol. This is what we say we're gonna do, and this is what we do.
Fair enough. I guess, yeah, I would be curious. Maybe I'll reach out with you afterwards just to, I'm not sure what these guidelines are. I guess you're right that the key is to do your, as you know, for our studies, we have clinicaltrials.gov often because they're interventions. And we put our foot down with that and then kind of use that to guide things. But I'd just be curious to see the other guidelines you mentioned.
I see. Yeah, yeah. So there are some reporting guidelines. They basically ask for that a few details of the experiment. Like for example, they will ask you that you have to mention randomization, how the randomization is done, and so you have mentioned that certain aspect of the experiment in the paper. So that's kind of reporting guideline, like a checklist kind of thing. Yeah.
Okay, you're talking about like the consort and the strobe and
Right,
these
right,
things.
right. Those things.
Okay, yes.
Yeah. And I think yeah, for these also that a lot of times that you see people reporting like secondary outcome and other things. So when we read that, we really have to that be a little bit cautious about that, because we know it's probably not controlled for type 1 error, and it's likely there will be some a lot of false positives.
I got a bigger question. Can you go back out to one of your first slides, list off all the choices?
Oh, okay, yeah. So let me here. This one, right?
That one.
Okay.
So my read is you haven't touched any of these other choices, because the solution here is once you've decided you're going to test a hypothesis, and it's a yes and no, this is a solution for that decision. It doesn't control for any of these other choices whatsoever. Is that fair?
Can you elaborate a little bit?
Well, because you've put this all into a 2x2 table, and your solution is around the error estimates in your 2x2. Well, what happens? That is only if we ask a yes/no question.
Right.
What happens if we got the question wrong? Meaning that, what if it isn't a yes/no question? What we should be asking is a question in medical trials is, instead of does it work or not, under what conditions does it work? And under what conditions does it not work? That changes the question completely. And right? So
I think that sort of reframed the hypothesis that so to me, it seems that's testing interaction, right? So with certain condition, the treatment work, and with other condition, the treatment doesn't work. And so it's the hypothesis is testing the interaction between the treatment and the condition.
Yeah, but what I worry about is we're often looking at really complex systems where the notion of causality of it's a single yes it causes or doesn't cause it kind of doesn't make any sense.
Right. I see what you're saying. Yeah.
Right. So all these other pieces are all the choices you make after you've picked that I want to go to yes, no. I mean, interpretations of things, of how the thing works in the world. Think of how our eyes work. Our eyes suck in huge amounts of information. And there's never a hypothesis per se, because we're balancing all of this stuff and we can interpret from where we're standing how that system works. And I sometimes wonder that the real problem isn't the statistics. The real problem is we don't really look closely at the phenomena we're studying and where we're looking at it from, because there is no yes, no in a system,
Right, right.
right?
Yeah, I see what you're saying. So you say that the problem is actually more complex than we can frame it as a hypothesis.
Yeah. I mean, if you look at what we see in evaluation of programs, this is moving away to some bigger, more complex things, programs, interventions. Instead of asking, does the intervention work or not, there's this sort of realist evaluation that says, don't frame it like that. Frame it under what conditions does it work for whom, where, when, and how. And then you move it more into the exploratory world, you would have a much better understanding, a more robust understanding of the phenomena you're looking at, as opposed to very fragile understanding of looking at one thing, thumbs up, thumbs down.
Right, right. Yeah, I certainly agree that exploratory analysis has its values. The problem is that we human beings, we are very good at explaining things away or justify everything. We're very good liars, and so that caused the problem. Sometimes, we believe certain things, and the consciously or subconsciously we make certain choices, and we don't even realize that that affects the result that we conclude.
So that seems to argue for a hypothesis test that's very rigid and very narrow, right? So we're going to control all this stuff out and get rid of our bias. But think of the paradox here. Liars are terrible at narrating a story because they keep all the pieces together. So what you detect liars from is actually they can't put the coherence in there, and you pick up the liar from more information spread widely as opposed to looking at super narrow.
Yeah, I see what you're saying, that liars probably they cannot complete a story, right? That's what you're saying, that they couldn't have. So the problem is, I think in science, the things that we understand are very limited. Most of the time, we couldn't complete a story.
True.
And so we couldn't tell, is that just that we lie, or it's just that we don't have enough knowledge?
Yeah, I think you're always going to have this tension here.
Right. Like for example here, that I don't think these people are intentionally to lie. It's just that, so these probably have something about regression to mean and other problem. Yeah, I see what you're saying. There's a lot of noise, and sometimes the problem is more complicated, and it's difficult to frame as a hypothesis. I guess the goal is to remove these the possible bias that when we do research. There are certain fields, right, that in a lot of social science they don't do this, right? They just have a theory, and they have some they use their intellectual reasoning to derive things, right? And yeah, I mean, I don't know those things very well. I don't know how it works, but probably I think there are some values to it too.
Well, I don't want to go to Gary's complicated world, which I like, but I'm just wondering what it makes me think about is significant individual change, which I've looked at. You can do the same thing there, say, is it significant or not for an individual? But there are some people who say you shouldn't do that. You should say probabilistic, they're more than 50% likely to have gotten better, or 60%, or, make it more of a continuum than just yes or no. And I know Gary's been saying a lot more than that, but I kind of wonder about that as well, rather than just having to say, yeah, it meets the 0.05 significant level, and we're confident that, it's unlikely to be due to chance.
Right.
This other world. of,
I agree. Yeah. So there's a hypothesis testing and there's estimation, right? So once it's estimated that for certain things, we can only estimate, right? And a lot of things we couldn't have a very rigid scientific investigation. For example, like you know, a lot of social science stuff, like the marriage effect. What's the effect of marriage? Like there's no way to do a very rigorous scientific investigation. And you can get it as close as possible, but I don't know if we can ever to get to the truth behind it. But I think that's what we should try to do, be a little bit more objective, and we if we don't say that it's impossible, then we just totally ignore this. We say that we try to accommodate this process as objectively as possible.
Right, but Ron, it sounds to me like you're pushing. It's not the p-value; it's actually the absolute risk reduction, and not the relative risk reduction. Right, between if you're looking at a drug or some sort of intervention or exposure, is at the end of the day, you're looking at that, and then you're going back to a probability, and you're saying the person in front of me has this probability based on what we came to from a sample to the general, and then you apply the general knowledge to the individual. So you want to stay in the probabilistic world, correct?
well, yeah, I'm not going to go into everything you just said, but I mean, I think people are thinking about this sometimes differently. They're not so stuck on an exact p-value. They just want to say, you know, is it more or less likely to be true, but not with an exact cutoff necessarily. I mean, they want to quantitate it a little bit.
Right.
I was just trying to throw it out there, but I know we're at the end of the hour. So
Right.
it's kind of related to what you said in some weird way, but not very much.
Yeah, there's a movement. People try to get away with p-value because a lot of times it just doesn't work very well, right? So there's some movement. So I think a company. So one way is accompanying with the p-value. We always present the point estimates, right? What's the effect, and that's important too.
Just wanted to thank Chi-Hong for joining us, and please remember to complete the evaluations. Art put the link in the chat. And yeah, everyone have a great afternoon, and we'll see you next month at the RCMAR methods talk.
Thanks, Jihan.
Thank you.
Thank you.
Appreciate it.
Bye.
Thank you, everyone.